Hello, welcome to the Sigma Made Simple channel. This channel is dedicated to explaining the principles of Lean Sigma and Six Sigma to anyone with little or no knowledge but wish to make improvements to a measurable process. My name is Dennis Wells, and I was learning about these tools even before I was certified in 2008 as a Six Sigma Black Belt and a Lean Sigma Green Belt in 2009. I have acted as a Master Black Belt where I mentored many engineers for their Black Belt certification, trained personnel, mentored interns, and trained managers on these tools. Even in semi-retirement, I continue teaching and learning as I believe in their power when applied properly. That is what I hope to show you on this channel. We will summarize what we've done so far and what we need to do next. So our agenda, we will review what we've done so far and then review the initial value stream map that we created a couple of videos ago. The questions will be answered that came about from that value stream map, and then we're going to talk about what to do next. So on day one, our team selected a product family, having 10 lines on 2 shifts, and brought all the operators in for a 1-hour meeting. We explained what we were doing, how important their role is, and created the initial value stream map. When reviewing the initial value stream map, we had some questions. Why is polish and crimp value added, but have a first pass yield less than 100%? Let me pull this up. We can take a look at it. So you see polish, 94% value added. 98% value added. Usually you'll have a first pass yield less than 100% if it's a non-value added or inspection point. So when we're reviewing the initial value stream map, we did notice this and we decided to investigate it. We also identified the top 3 bottlenecks and the need to verify their cycle time, as the value stream map output was not the same as the historical data. The 3 bottlenecks were polish was number 1. If you look at line 16, the workstation factor, this takes into account all kinds of variables, including rework that might be sent back upstream to this workstation. So polish had a 189.8. Then geometry was the next bottleneck at 158.1. And then the next bottleneck was loss at 124.4. And if you notice, pretty much everything else other than those has a much lower number. Let's scroll over here. So we decided to look at the historical data, and this is why. Our output for this, our output for the historical data was 391, and we decided to verify that. So we looked at the data. I showed you that in an earlier video. We did verify the output as being 391. We picked one line, line 3, shift A, and we looked at the data, and that's what we created, and that's what we decided on. We did find that the data was a changing trend. Or, I'm sorry, it wasn't a changing trend. It was a multi-frequency. So we have to keep the lines and the shifts separate. So the top 3 bottlenecks, like I said, were polish, geometry, and loss. And we're reviewing those cycle times because this 391 has been verified as being accurate, did not match with what our value stream output was. Our value stream output on line 26 was 28 to 285. It has to be within 10%. In this case, it's not usable. So we knew we had something wrong somewhere. I'm going to go on to the next. So on day 2, we reviewed the historical data, like I said, and found that it was a constant trend with multi-frequency by shift. We created eye charts for all the lines and all the shifts. And then we created a consolidated spreadsheet. And the eye chart looked like this. And it was really simple for the operators because they just click this button and then here, I'll do that. We'll click the button. They put in a number and it tells them if there's something going on. And then they can contact somebody. Or better yet, every day an engineer would be reviewing the consolidated eye chart, and that would be telling them if something was going on. This comes directly from those eye charts. So what the engineer does every day as well is he creates a Pareto. So anything that's got a reason, and here there's no work, ran out of work, no work, they start creating this Pareto chart here. We're only going to track the first few types of errors, and then that gives us an idea what to work on in the future. Each one of these tasks takes about a minute, unless maybe there's some statistically significant event showing up here in green or in red, and then they would be investigating that. Like I said, line 3, shift A was selected to answer the questions, and day 2 was spent verifying the cycle time at polish, geometry, and loss, as well as why polish and crimp are value added and have a first pass yield of 100%. So we found that polish actually has 2 workstations. I'm going to jump back over here. I go to the current. What we found was that polish actually has 2 workstations that should be separated. One workstation would keep the name polish at a cycle time of 115 seconds per connector, and then a new workstation would be putting the value stream map for end face at a cycle time of 50 seconds per connector. So what we did was we started filling that out in the proposed. So here's the proposed. So we broke polish and end face down into 2 different separate workstations. End face is now non-value added. It's got 94% yield, and it goes back to uh, position 3. There's a 3 here, and that goes back to polish for 3. So what we found was also that crimp was value added, and that's because the operations are kind of difficult. It's easy to break a fiber. It's a delicate process. So we do have a value added workstation here with a first pass yield of 98%. This is an opportunity for improvement with design or with processes. So the proposed tab has a starburst here, just to remind us. So we probably need to look at that. It turns out there was an issue with writing down some data in our meeting at geometry, and the cycle time should have been 95 seconds, so we updated that. And we also found that loss has a cycle time of 122 seconds. We verified that. But there's a lot of recovery. And recovery is when you have to do something to a non-conforming product to make it conforming. It usually adds to your cycle time. Here, as the operators retest, they can retest up to 7 times before they actually fail something. And then you get that's usually due to end face cleanliness, debris, keeping an end face from mating with another end face. So we're going to leave a starburst there as well because we want to do something about that. So with the updates and the changes for our value stream map, the output of the value stream map is actually within 10% of the output. I'm going to show you that by copying this. Excuse me. I copy all this over here. And then I'm going to put it in the current because we've corrected everything. And then if you look at the base data here, the output was verified at 391. That's what we're going to use. And then the VSM output on line 26 has 408. That's within 10%. So this is a usable value stream map. It should be pretty accurate at predicting changes in your process. So we do have some opportunities for improvement. We're going to look at the current tab again. So what you notice here is that the workstation factor for polish and for loss are within 10% of each other. So we're gonna have to work on both of those workstations at the same time, improve both of them. And what is a good goal for that? Well, if we look at our third bottleneck, geometry is 103.6. What I usually like to do is work on the top 3 bottlenecks, try to get them below the next one. And if you look at this workstation factor pot, is the next bottleneck at 98.8. So what I do is I try to see how close I can get polish and loss and geometry to the 98.8. I give them all the goal of getting their cycle time to less than 98.8. And they can do that by, like in polish, maybe they can take some of the items that the polishing operator is doing and have the in-face operator do those instead. Same with loss or geometry. You can look at adjacent workstations and see if you can move some of the operations around. You would do that by creating a value stream map for polish, then a value stream map for in-face, and look at the things that polish is doing that maybe the people at in-face could do to help them out. Same with loss. Is there anything at the loss station that the person doing crimp can help out with? Or is there anything at geometry that the in-face person could work with, or anything at geometry that the crimp person could do for them? That's one way. You can also look at process improvements. So we're going to try to get our top three bottlenecks to 98.8 seconds or less. That's our target. So let's look at what if we did that. So what's nice about this is now that we know we can measure things, if you look at the base data, since we copied and pasted the current or the proposed data into the current, these are basically identical. 88, 64, 85, 49, and then the prices. So what we can do is we go to proposed and we can say, what if we do get these workstations down to 98.8? And we can do that one of a couple ways. We can either put 98.8 in here, or we can just remove this. And we're just going to remove the numbers, this workstation factor. And then what that's going to do is that's going to make the 98.8 our maximum workstation factor. Then we can go back and look at the base data. And what that says is we're going to improve our performance to 69.4. Let's see if we can zoom out a little bit here. So our performance was 64.8. Now our performance goes up to 69.4. Our OCE increases from 49.1 to 52.5. We're going to save about $1.14 per connector. Overall, we're going to save $137,000 per line. We got 10 lines, so that's $1.3 million. So that's quite a bit of money that we can save if we can get those workstations down below that threshold of 98.8. So what we'll do is we'll create some Six Sigma projects and Lean Sigma projects for polish and for geometry and for loss, looking at how we can improve those. And we're going to show you that in the next video. We're not going to go into detail in this video because this video is just talking about finding the opportunities. So we'll give those three projects the goal of being less than 98.8. But if you take a look at the average for all of these workstations, let's go back to the current. Let's take an average for the workstation factor. And our average is 85.7. So we're going to make a stretch goal of getting everything below 85.7. If we can get those three below 85.7, then our next bottleneck is actually going to be potting, and then it'll have a goal. But that's a stretch goal. We're going to stick with 98.8 for now. So to do this, we start by using an eye chart we created for line 3, shift A, on all 10 lines for all shifts. This will be 20 eye charts, where the line leader will use a link to their file to input the data at the end of each shift. Engineers will check the summary sheet each day. Both tasks should take less than a minute if there's no statistically significant events, but there will be statistically significant events in the beginning because not all lines and shifts are going to perform the same. What you're looking for are the lines that are outperforming according to this eye chart, or lines underperforming. I'm going to show you that in a second here. And here's how, when you open this up, it automatically updates from all the other spreadsheets. It tells you who's outperforming, as in the green, and who's underperforming, as in the red. And you'll notice that there's a comment in here, ran out of work, no work, nothing on at the beginning of the shift, nothing on the line, no work, and then they were shut down. So, and maybe you can't do anything about it, but you can start creating your Pareto charts, and you can tell people, hey, managers, we didn't have enough work this day. That caused us this amount of issues, and the line was run dry. It happened once. You can start using that to look at for other areas where you can make improvements. So use this sheet here to look for the statistically significant events and then investigate why. See if you can use or learn from the outperforming, the lines and shifts that are overperforming. See if you can figure out what they're doing differently and get all the other lines and shifts kind of performing the same. Eventually, you should have basically everything here with nothing statistically significant rather than a green or red. You might have some red because you're out of materials, out of work, especially when you start running at a higher rate. You're going to run your materials out much more quickly, which is a good thing, but you still want to note it. And then you can tell people who are in procurement, who are probably already working on it, how much it's affecting you guys. So the engineer is going to use a summary sheet to find that, and then and use the Pareto chart to find areas where you can make improvements. So then over time, what's going to happen is all the lines will start performing the same. Now, this is going to happen while you're working on those other Six Sigma projects, because those projects are going to take anywhere from 6 weeks to 6 months, depending on how difficult they're going to be. But eventually, what's going to happen is you're going to find these better performing lines. You're going to run this for at least 10 days so that you can hopefully get everybody kind of aligned, doing everything the same way. And then when you're done, everybody's going to probably be outperforming. And then you're going to have to go back and recalculate your mean and your control limits. That's not difficult to do. I showed you how to do that earlier, so you should have no problems with that. You continue using these eye charts because as you start making changes in the future that will affect all lines, you should start seeing every line turn green and telling you that they're outperforming. Some of these opportunities that you're going to experience are going to be beyond your ability. You're still going to track these and report them. Things like no orders released due to low volume of orders. You'll tell management materials in the bombs are not available. Tell procurement. Personnel not available, tell management, and that's going to lead you to start using another tool, which is standard work. We'll talk about that in another video. All line leads and engineers should have standard work. It's a basic lean concept. So at the same time, we're going to open up those 3 Six Sigma projects. And we keep chipping away at our cycle times. What we eventually want to do is get everything level loaded, and then we'll be in good shape. So while we're making changes to the lines and all the shifts to bring them up to the same highest performance, we started those Six Sigma projects. We took a few weeks, and I'll show you how to run a Six Sigma project in the next series of videos. For now, we're going to look at the results of these efforts to show you how they relate to the value stream map. It was realized the value stream map was a good idea at Polish to see what parts of the process could be moved upstream or downstream. In the polish station, we simply took some of the work from the polisher and had the in-face operator help out. This lowered the polish cycle time to 90 seconds, reduced by 25, and then in-face was increased by 25. I'm going to pull that up now. Here it is. So you can see polish was reduced to 90 seconds. In-face was increased by 25, so it went to 75 seconds. Workstation factor for polish was reduced to 103.5, so they met their goal. Well, not quite met their goal, but they're getting close to it. Made good progress. Loss testing had a Six Sigma project that reduced the number of recovery attempts from 7 to 3. I'm going to slide over here. The cycle time went down to 91 seconds. And then so the workstation factor went to 92.8, which is below the goal. So they did a pretty good job on that one. And it turned out that the solution that was used at loss testing could also be used at geometry. So it was having to do with the cleaning, and it was reduced. The time was reduced to 90 at the workstation. Factor was reduced to 98, 98.1. When we update the proposed tab, weeks before the implementation, we expected an increase in output of like 30 some percent. And if we look at what we did now, we didn't quite reach it. But what we did do is we did decrease the times, and this was what we had originally. This is where we're sitting now. We're looking at a pretty good change of 112,000. So for 10 lines, that's 1.1 million. We still got a little ways to go because we still want to reduce polish. But for now, we'd probably, these things we probably got done within a few weeks. So this is pretty much your continuous improvement cycle. So what you'll do is you'll identify some projects, you'll work on those, then that's part of the plan, and then you make one change. Like for this series, I showed you a couple of changes, but we would first make the change for polish by moving some work over to the end face, and then the times changed, and then we would verify that change. And once the spreadsheet or the eye charts verified the change, and we got another stable bit of data that we can recalculate the means and the standard deviation, that tells us how much we're saving. Then we made another change. That would be the loss testing station. And we reduced that time. And then we verified that that change had the effect we wanted with the eye charts. And then we made the change on geometry, and we verified that with the eye charts. That's your plan, do, check, act cycle, PDCA. That's another Lean Sigma uh, ideology here is we planned by looking at how we're performing and deciding on what we want to look at. We made a change, we checked it with the eye chart, and then we acted by making another change. We noticed that our OCEs have increased, and our costs are going down. So the next video will show you an idea on how to increase your availability portion of OCE. It's often overlooked as something that cannot be helped, but there are ways to increase this, even marginally, and it doesn't cost you anything, just takes a little time. So if you found this video useful, like it, subscribe to the channel, and share it with anyone else who may find it useful. If you didn't find this video useful, then subscribe in the hope that an upcoming video will be useful. Eventually, we're going to go through projects using Lean Sigma and Six Sigma tools, as well as the tools needed to support them. Remember, a wise person learns from their mistakes, while a genius learns from the mistakes of others. We'll see you soon.